Welcome to the final course in the PyTorch Professional Certificate, Advanced Architectures and Deployments with PyTorch. In the previous two courses, you learned the fundamentals while building and optimizing models that can tackle real problems. In this course, you learned about creative ways to put together neural network building blocks in PyTorch to build advanced architectures like you hear about the Siamese net, ResNet, DenseNet. And these more advanced architectures are great for specialized tasks like, you see, deciding if two signatures match or if two pictures of faces are of the same person. So when you finish this professional certificate, you'll be ready to tackle, with a fairly cutting-edge way, many of the practical challenges that businesses are facing today.
So there's 4 modules. In the first one, we're going to look at the custom architectures that Andrew was talking about, models that can branch, share information, and even adapt their behavior. Along the way, we'll look at the Siamese networks, ResNet, and DenseNet. Then in module 2 is where I'm geeking out, and we're going to focus on vision. And we'll look at the techniques that really reveal what parts of an image a model is focusing on. And we'll experiment with some of those same ideas. Then in module 3 is the big one. We'll move on to language, and we'll look at the transformer architecture itself, the encoder, the decoder, and the encoder-decoder, and all of the attention mechanisms. In module 4, we're just going to pivot in how to prepare your models for deployment. The things that you do, for example, to compress them and quantize them, and the trade-offs that you have to make in doing that, and in making them efficient enough to serve real users.
With this final course of this professional certificate, I think you come away able to get really much closer to the cutting edge and tackle practical problems that very few teams in the world even knew how to do just 1 or 2 years ago, especially with the open source offerings that you now be able to take advantage of with this skill set. And so to get started, in the next video, Lawrence will show you why the sequential architectures that you learned about so far sometimes has limits, but also how PyTorch gives you flexibility to give architectures that solve problems using a more complex architecture. So let's head over to the first video and get started.
In the last video, you saw that PyTorch models are not limited to a single linear chain. Your forwards can accept multiple inputs and return multiple outputs. You can reuse the same module instance by calling it more than once, and you can use ordinary Python control flow in forward because your graphs are defined dynamically. Now you're going to see how those same ideas show up in real architectures. Let's start with a problem that inspired a classic architecture that breaks the linear path. The problem? Comparing signatures. Say a bank has your signature on file. So when you sign something new, they need to check whether it matches what's on record. It sounds like the sort of thing a simple classification model could handle, but once you try to set it up that way, you'll quickly find that it's not so straightforward. The problem is this: the thing being classified is your handwriting. So a per-person classifier needs many labeled examples for each person before it could reliably learn to call something yours. But the bank likely doesn't have that. They may only have one signature on file. Yet the bank has a model that's able to decide if that new signature is really yours. So how would you even train a model to pull this off? If the bank was using a per-person classifier, they would need labeled examples for every customer, and that's not realistic given how few examples each person will provide. And here's the kicker: every time a new person joins the bank, a standard fixed label classifier would have to be updated, often retrained, because it needs to add a new class and learn how to separate that person from everyone else. For a real bank, that's just not practical. So what if, instead of asking, whose signature is that, you asked a different question? And that question is, do these two signatures come from the same person? Now that will flip the whole setup. Instead of memorizing individuals, the model can learn a similarity function, and that is a general skill for deciding whether two signatures are by the same person, even for writers that it hasn't previously seen. A standard way of accomplishing this is to pass both signatures through the same encoder, often a CNN for images like signatures, and they'll have shared weights so that their features are directly comparable. Now that's just parameter sharing in action like you just learned in the last video. In the lab, you'll see a slightly richer setup with 3 inputs at once: an anchor signature, like the one on file, a genuine match, and then typically either somebody else's signature or a forgery. So now let's see what that looks like in code. First, inside getItem, the steps are simple. You sample a person, grab two genuine signatures, one becomes the anchor, one is the positive, and then you'll choose a negative. That triplet is what you return for training. And remember, all three will go through the same encoder so that they land in the same feature space. So now when the data loader assembles a batch of these triplets, you'll feed them into the Siamese network. Next, in the init of the Siamese network, you can pass in this embedding network that's defined outside of the model, as you'll see in the lab, and you'll set it to self.embeddingNetwork. Then, inside forward, the anchor, positive, and negative will all run through that same embedding network. And that's parameter sharing in action. One network reused 3 times on different inputs. The result? 3 embeddings, one for each signature, encoded in exactly the same way so that they can be compared directly. Now what's interesting is that typically the model would stop there. It doesn't spit out a yes or no answer about whether signatures match. All it does is turn each signature into a representation that makes them comparable. The comparison happens in the loss. During training, the loss pulls the anchor and the positive closer together, and it pushes the anchor and the negative further apart. So how do you actually write a loss function that does that? Well, usually you'll see 2 options: contrastive loss for pairs and triplet margin loss for triplets. Both of these serve the same purpose. They teach the network to make the numbers for a genuine pair come out closer together and the numbers for a non-match farther apart. If you peek inside a simple contrastive loss class, you'll see it's just really a few lines of code. Now, you don't need to fully understand this loss function to use it, but here's the key idea if you're curious. It measures the Euclidean distance between the 2 outputs, treating them like points in a space. If the label says same, the loss uses the squared distance, so the model learns to pull them close. If it says different, the loss applies a margin so that the model pushes them apart, but only until they're far enough. Past that cutoff, there's no penalty. It's a bit like magnets. Similar pairs attract, different pairs repel, but only to a certain point. But really, it's just distance math wrapped up in a pytorch nn.module. The built-in triplet margin loss works in almost the same way, but just with 3 inputs. Instead of looking at labels, it compares distances directly, making anchor positive closer than the anchor negative and with a margin in between. Well, if that feels confusing right now, don't worry. You'll see more in the lab, and you can dig deeper in the course resources if you're interested. And finally, the loss is used during training as usual, like this. So that's the idea behind a Siamese network. Instead of classifying each input, it compares 2 inputs and decides whether they're similar based on whatever your definition of similar is. This same pattern shows up in all kinds of places, comparing faces, matching voices, and even checking whether 2 sentences mean the same thing. It's also a design that you generally do not build with nn.sequential because you want to write a custom forward for the parallel weight shared branches. So check out the code, give it a try, and see how this kind of model works in practice. Then, in the next video, you'll explore another important architecture that solved a long-standing problem in deep learning. Hope you enjoy the lab, and I'll see you next time. In this module, you're exploring how custom architectures in PyTorch can solve problems that plain sequential models cannot. And you just saw one example, a Siamese network. Instead of training a separate classifier for every category, it learns a general way to measure whether 2 inputs are similar: images, voices, sentences, or anything that you might want to compare. But not every architectural challenge comes from the task itself. Sometimes the design is shaped by how the model learns. That's exactly the case with the next architecture you'll explore, ResNet. It doesn't use multiple inputs or shared weights like the Siamese network. Instead, it introduces a new pathway inside the network, built to handle problems that appear when models get very deep. Okay, I know that might sound strange. After all, you might think the deeper the network, the better it should be at tackling complex problems. But in the early days of deep learning, researchers found that very deep networks often ran into serious problems until this custom architecture changed the game. One such problem was that as networks got deeper, the early layers stopped learning, or at least they learned much more slowly. And this is a byproduct of backpropagation, the signals that flow backward from the loss through each layer towards the input. The deeper the network, the longer that journey, and the signals could fade as they traveled, like a message getting weaker the further it goes. To really understand what's going on, you need to peek at a little math. And yes, I know it's calculus, but don't let the symbols intimidate you if your math is rusty like mine. The idea is simple, and I'll try to keep it straightforward. So, as you know, each weight in a network has a gradient. Think of it like a slope, how the loss changes if you nudge that weight. Formally, it's the partial derivative of the loss with respect to that weight. But here's the key point. To get a weight's gradient, you walk backward through the network. You start at the loss and pass through each layer's gradient along the path to that weight. It's a little bit like a game of telephone, one step at a time. Now, the math behind that chain is a long product of derivatives from each layer. Each step multiplies in another factor, and that's how you get the gradient for the weight that you care about. But here's the crux. Many of those terms, like activation derivatives and scale factors, are less than 1. And when you multiply a bunch of small numbers together, the result gets smaller and smaller. So, the deeper the network, the more those gradients shrink. And by the time the signal reaches the earliest layers, it can be so faint that the weight updates are tiny, so small that they barely change the weights at all. In practice, those early layers learn very little and sometimes stop learning altogether. This is known as the vanishing gradient problem. Before ResNet, training beyond a few dozen layers was extremely difficult, but ResNet changed all of that, showing for the first time that networks with over 100 or more layers could actually be trained. But vanishing gradients were not the only problem. It might seem that if deep networks don't learn, they're at least harmless. But researchers found the opposite. Adding layers often made models perform worse. So how do you fix a network that fails just by being too deep? Well, let's find out by tracing through the code. In the lab, you'll work with a model called Simple ResNet. Let's start at its forward method and follow the trail to uncover what makes this architecture different. At first glance, it looks like expected, modular blocks all stacked up. The initial block and final block are nothing unusual, just a conv up front and a linear at the end. So, if you're looking for what makes this model special, the trail leads to the res blocks. So let's check out the forward method of a residual block. First, you have identity equals x, and that's interesting. You're making a copy of the input and sending it to something called initial forward. And that is just 2 convolutional blocks, so there's nothing unusual there. So back in the forward, you have a check that seems to downsample x. We'll set that aside for a moment, it'll make more sense later. And now, something very simple and very interesting. You take the output and you add the original input back in. Surprise, that's it, that's the magic. This is a residual, also called a skip connection. It's almost underwhelming. Add the input to the output. But this small change can make training networks with hundreds of layers possible. But before explaining how, let's get downsampling out of the way. It's very simple conceptually. If the output has changed shape, you just adjust the input with a downsample so that it matches. And that's it, because those shapes need to line up if you want to add them together. But now, the key question. How does adding the input back to the output actually help with vanishing gradients? And here's where a little more calculus shows up, but I'll keep it simple. Let's start without the residual. So a normal block takes some input x and applies a function f of x, and will represent the derivative of this function like so. So, during backpropagation, you saw earlier that calculating the gradient here is really just a long chain of derivatives multiplied together, ending with this final derivative. But let's just think of the chain as one value representing the product of all previous derivatives before being multiplied by the final derivative. This here is just the standard gradient calculation that will tell you how a tiny nudge to x will change the loss. But now let's compare it to a residual connection. The output of your block is now f of x plus x. And if you're going to get the derivative of this, and if you know your calculus, it becomes f of x prime plus 1, which means the gradient is now the chain of derivatives multiplied by the final derivative. So let's expand that to get the following. That's very interesting. This first term is the same as it was without a residual connection, but now you've got this extra plus chain of derivatives. So instead of the gradient being squeezed smaller and smaller through multiplications, it's getting that direct boost, almost like a nudge from the original chain, and that keeps the signal alive. And that's why people say residual connections preserve the gradient, so it doesn't degrade over time. So even if your math is rusty, the big picture is simple. Residual connections boost the gradient so that they do not fade away, and that's what makes very deep networks trainable. And if you want to dig deeper, check out the resources. Now, one more interesting point. Residual connections also shape the forward pass. If the input is added back to the output, the block is not building something new, it's just nudging the input. So think of it as input plus correction. So instead of asking, well, what should the output be? The network now asks, what needs to change about the input to move it closer to the right answer? Each block will just nudge it along step by step. This makes learning easier and more stable, especially in very deep models. The input signal is preserved, not overwritten, so early features stay available all the way through. Each layer just refines them rather than trying to reinvent them. And all of this is why ResNet was such a breakthrough. Before it, networks deeper than about 20 layers didn't just stall, their training error actually got worse as depth increased. ResNet changed all of that, showing for the first time that networks with hundreds of layers could be trained successfully. And that leap reshaped deep learning research. So now you've seen how residual connections both solve vanishing gradients and change the way that networks learn. Next, it's your turn. In the lab, you'll train a simple ResNet and see firsthand how this one line of code changed the way deep networks can be built. Welcome to Module 2, Specialized Approaches to Vision in PyTorch. In the last module, you explored custom architectures such as Siamese networks and ResNet, focusing on what made their designs unique. In this module, you'll explore specialized approaches for vision, from deep CNN architectures to interpretability tools like saliency maps or class activation maps, and we'll look at generative models such as diffusion ones. You've been working with convolutional networks ever since Course 1, and you may have noticed that most filters will only look at a small 3x3 neighborhood at a time. But have you ever wondered how, even with filters that small, your model is able to pick up both the tiniest edge and the overall shape of an object? How could both of those things be true when the filter size never really changes? And that's the puzzle here, and it points to deeper architectural challenges. How do you get filters that effectively represent different sized chunks of an image? It might sound mysterious at first, but the answer turns out to be simple. It's just the same PyTorch layers that you've already been working with, arranged in a clever way. But before you see how the puzzle plays out, it's worth pausing for a quick reminder of what makes convolutions different from fully connected layers in the first place. Because that difference is exactly what makes this whole trick possible. Think about a standard image. A 224 by 224 RGB image has over 150,000 pixel values. If you connected all of those directly to just 64 neurons in a fully connected layer, you'd need almost 10 million weights in that first layer alone. Now that's a huge number of parameters to train, which slows learning and makes overfitting much more likely. Convolutions will handle this very differently. Instead of learning a separate weight for every pixel at every location, a convolutional filter learns a tiny patch, say a 3x3 area, across the 3 color channels. So that's just 27 weights plus 1 bias for the filter. That part you already know, and it's a clever trick in its own right, is that you slide that same filter across the entire image. Instead of treating each pixel on its own, the filter will always look at neighboring pixels together. And you don't just have one filter doing this, you have many. And each of these will learn a different kind of pattern, like an edge, a corner, or a texture. And once a filter has learned to detect a feature, say the edge of a cat's ear, it can recognize that feature no matter where it appears in the image. And that's just the starting point. The real question is, how do those small patches add up to filters that act like they're seeing much larger portions of the image? Well, let's make that concrete. Imagine you start with this 96 by 96 image of a cat. In the very first convolutional layer, each filter is only looking at a 3x3 patch of pixels, that's 9 pixels in total. Each position in the resulting feature map depends on just that small neighborhood of pixels from the original image. If you change any one of those pixels, the number at that position in the feature map will change too. Now that patch has a name. It's the receptive field. And at this stage, the influence is very local, only the pixels inside that tiny window. And here, in the feature maps of the first convolutional layer, the visualizations sometimes look a lot like the original image, but what they're really capturing are simple local patterns like edges or textures. Now let's see what happens when you add more layers. Suppose you take that first set of feature maps and run them through a pooling layer, say a 2x2 pooling with a stride of 2. That will reduce the map from 96 by 96 down to 48 by 48. It's helpful to picture this as laying out a 48 by 48 grid over the original image, where each cell shows the coverage of only one position in the new feature map. You can think of each new cell as lining up with a 2x2 patch of the pixels. In other words, each position in the 48 by 48 map now represents 4 pixels in the original image. Now here's where it gets interesting. When you follow that pooling step with another 3x3 convolution, you're now applying the filter on this new, smaller feature map. And remember, each position in that map already represents a 2x2 patch of the original image, not just a single pixel. So when your 3x3 filter slides across this pooled map, it's no longer looking at 9 individual pixels of the original image, it's looking at 9 pooled cells. And each of these cells covers 2x2 original pixels. Now that means that the same 3x3 filter now spans a region that lines up with 36 pixels of the original image. But that 36 is just the starting count. Each pooled cell in the 48 by 48 map wasn't a clean 2x2 copy of the original pixels. That pooled value has already been influenced by neighboring pixels through the earlier 3x3 filter. So, when you trace things back, you're not only counting the pixels directly under the new 3x3 grid, but also the nearby pixels that bled in along the way. And that's why the receptive field at this layer is actually a bit larger than 36. But compare the coverage of this 3x3 filter to the original 3x3 filter, the same sized filter now corresponds to a much larger patch of the image. And if you keep going, the effect compounds. Add another pooling layer and your feature maps shrink again, from 48 by 48 down to 24 by 24. Apply another 3x3 convolution on that new map, and each filter now covers an even larger patch of the original image. Stack one more round of pooling and convolution, and you're down to 12 by 12 maps. At this point, each single value is influenced by a huge portion of the original pixels, even though the feature maps themselves keep getting smaller and smaller. That's the key pattern to notice. Every time you add layers like this, the receptive field grows. The network's view of the original image will keep expanding, while the maps themselves shrink. And if you look at those deeper feature maps, you'll notice that they feel much more abstract. Early layers light up for edges and textures. Deeper layers respond to larger patterns, curves, part of objects, even combinations of shapes. And if you go deep enough, a single activation can depend on the entire image. Now, to be clear, not every model will grow its receptive field in exactly the same way. The ResNet model that you'll explore in the lab won't line up perfectly with this example. Choices like stride length, kernel size, padding, and the overall layer arrangement will affect how quickly the receptive field expands. In fact, in some architectures like ResNet, the receptive field can even extend beyond the image itself. And by the time you reach the deepest layers, the feature maps may look like little more than abstract patterns. But to the network, those patterns reflect large combinations of shapes across the image. And it's the evidence it needs to decide this is a cat. That's the power of deep CNNs. As you go deeper, the maps get smaller, the receptive fields get larger, and the network moves from tiny local details to a complete, integrated view of the image. It's how a model can take pixels that only hint at an edge, connect those into curves, link those curves into parts, and finally recognize an entire object, all without you ever defining those parts yourself. In the lab, you'll dig into ResNet and receptive fields in more detail using pytorch. You'll visualize how feature maps evolve from layer to layer, and you'll see how receptive fields will grow across the network. And in the next video, you'll use that understanding to interpret which parts of an image your CNN focuses on when it makes a prediction, with tools like saliency maps and class activation maps. See you there. You've seen how CNNs build up features layer by layer, from edges to parts to whole objects, and how receptive fields will grow as you go deeper. Now, imagine a photo. You pass it through a model and it comes back with a prediction. That's a Labrador retriever. But how did the model make that decision? After all, to the model, the image is just a grid of numbers, and that's all the model will ever see. Somehow, from all of those numbers, it arrives at that label. So have you ever wondered, could you actually measure which of those pixels had the biggest influence on the prediction? The answer is yes. There's a whole family of techniques called interpretability, and these are methods which reveal which part of the input most affected a model's prediction. And while that might sound complicated, at the end of the day, they're just creative little solutions to an interesting problem that can be built and understood with the same PyTorch tools you already know. But why would it matter to know which parts of an image most influence a model's prediction? Well, there's a few reasons. First is trust. In high-stakes settings like medical imaging or self-driving cars, people want to see what guided the decision before they rely on that decision. Second, debugging. You can catch when a model makes the right call for the wrong reason, like you saw in Course 1, where a model predicted a wolf in the image because of snow in the background. Third, discovery. You can reveal surprising patterns, the kind of details that no one had thought to look for until the model brought them into focus. And finally, ethical concerns. These techniques can surface when a model behaves differently across different groups of people, and it's important to know that before you put it in practice. So, in short, interpretability gives you a way to peek inside and see what's driving the call. And let's start with one of the simplest interpretability techniques, saliency maps. So, imagine you've got a dog photo and the model predicts dog. Now, picture nudging one pixel in that image, and if that tiny change would noticeably raise or lower the model's score for dog, then that pixel is important for the prediction. And that's what a saliency map shows, as you can see here. The pixels that strongly affect the score will show up bright, and pixels that barely matter stay dark. So, how does PyTorch actually figure all of that out? It's the same process you've seen during training, calculating gradients. In training, those gradients are usually for the model's weights. And as you know, the gradient on a weight tells you how much changing that weight would change the model's output and ultimately the loss. But those are weights. What we really want here is something different. how much a change to an input value, the raw pixel number, would affect the overall prediction. But an input pixel doesn't have a weight attached to it. Is it even possible to get a gradient for an input value? Well, yes. Any tensor in the computation graph can carry gradients, and not just the parameters. You just need to set requires grad on the input image, and then backpropagate the score for a class like dog, and PyTorch will fill in the gradients on the pixel itself. And that gives you exactly what you need, a number for each pixel that says how sensitive the prediction is to a small change in that value. So when you see a saliency map, you're looking at those input gradients lined up with the pixels of the image. Big gradients mean that the pixel has a strong local influence on the score. Small gradients means it doesn't have much influence. But keep in mind, this shows sensitivity, not causation. A bright pixel does not prove that the model looked at features the way that a human would. It only means that the class score is especially sensitive to changes here. The nice part is this. In PyTorch, it's only a couple of lines of code to create these saliency maps. And you already know the steps: forward pass, backward pass, and grabbing gradients. And here, you're just pointing them at the input instead of the weights. In the rest of this video, you'll see how it works in code, and you can explore the full implementation in the lab. But I'm just going to focus on the key steps. First, put the model in evaluation mode. Models like ResNet use batch normalization, and some models also use dropout. In training mode, these will behave differently, and they can add randomness, which will make your predictions and your gradients jump around from one run to the next. Setting the model to eval mode makes sure that the saliency map will reflect the trained model. Now, load your image, like dog.jpg, and you'll turn it into a tensor that the model can work with. It's resized to 224 by 224, it's normalized with the standard values, and it's now ready for a forward pass. So now let's walk through the helper function from the lab. Compute salience map. This is where the saliency map actually gets created. It takes 3 inputs: the model, your image tensor, and an optional target class. Let's look inside and see what happens step by step. So the first thing to notice is this new line of code: input_image.clone.detach. Well, what's going on here? Well, remember, you want gradients on the input tensor. But PyTorch has a hidden twist. To save memory, it only keeps gradients for tensors that actually matter for training, like your model's weights. If it tried to store gradients for every intermediate result in the forward pass, your memory would fill up almost instantly. That means if a tensor is the output of an operation created from other tensors, PyTorch will treat it as an intermediate. Intermediates still pass gradients backwards, but they don't keep their own gradients. .detach breaks the history, and .clone makes a fresh copy. Now that will give you a clean starting tensor, and PyTorch calls this a leaf. Once the tensor is reset as a leaf, you can tell PyTorch to track gradients for it with requires grad, and then you'll run your forward pass. Now comes the key step. The output is a batch with one sample, where each entry is the model score for a different class. By writing output 0, target class, you're indexing into that tensor to grab the score for a specific class, for example dog, given this input. Then calling .backward on that single value tells PyTorch to calculate the gradients of that class score with respect to everything it's tracking, which now, importantly, includes the input pixels. Next, you can pull all those gradients out of the input tensor with this line of code. And what you get back is a 3-channel gradient map, showing how much each pixel influenced the model score for that class. That's exactly what you're after. So when you visualize it, you can overlay the saliency map on the original image. You'll see, for example, that the pixels around the dog's face contributed mostly to the model's decision. Pretty neat, right? So to recap, a saliency map is just the gradient of the class score with respect to each input pixel. Large gradients mean the prediction is especially sensitive to that pixel. It's a pixel-level view of what drove the model's choice. So in the next video, you're going to look at class activation maps. And this is a different method that highlights regions instead of individual pixels. And then in the lab, you'll try out both techniques to see how they compare. So far, you've been building and training models to make sense of images, classifying them, and revealing which regions mattered most for your predictions. But now comes a new challenge. Instead of making sense of images, what if you asked the model to create images? Well, for a long time, that turned out to be a really tough problem. Early methods for image generation came with major trade-offs. Some produced blurry results, others were unstable to train, or maybe far too slow to be practical. The search for a better approach led researchers to a surprising inspiration: thermodynamics. In particular, diffusion processes where particles gradually spread out over time. For example, think about what happens when a small cloud of gas is released in a room. The molecules will scatter randomly until they're spread evenly throughout the space, and while each particle moves unpredictably, the cloud as a whole follows neat probabilistic rules. So in theory, at least mathematically, you could describe the process in reverse, like running time backwards. Now, you can't reverse the process for the gas cloud, but an image is just numbers. So maybe if you start with a noisy image and run the diffusion process backwards, you could get a clean image in return. And that's exactly what diffusion models do to generate images. To understand how, let's look at the forward diffusion process, the very thing that the model is going to learn to reverse. Do note that in the early days, this was applied directly to pixel values, but more recent approaches often use a compressed representation called a latent space, and you can check out more in the course resources. But whether it's pixels or latent space, the process works the same way. And here, I'm going to use pixels because they're a little more intuitive. So in this setting, an image is just a tensor, basically a grid of numbers. At each step, you add in another tensor of the same shape filled with random values, which slightly shifts the originals. Those random values come from a Gaussian distribution, meaning most of these random shifts are very, very small and only a few of them are larger. Repeat this step again and again and again, and the picture will get fuzzier until eventually it looks like pure static. So now your goal is to start from that noisy image and take one small step backwards again and again and again until the image gradually comes back into view. It's kind of surprising when you think about it that most generated images that you see today began this way, as pure noise. So how would you even train a model like this? So let's start at the top. What do you think the model predicts? If you're feeding in a noisy image and a time step marker, literally an integer telling the model how far along it is in the diffusion process, how many random shifts have been applied so far, that kind of thing. So what comes out of the model? I encourage you to think about that and take a guess. Do you think the model tries to predict what the image looked like one step earlier? Well, no, that's not it. The output isn't a new image at all, it just predicts the noise. So think of it like this. The input image you gave the model could technically be thought of as some earlier image with a tensor of values representing the noise that's added to it. So now the model's job is to predict that tensor of noise values. But when I say the earlier image, well, how much earlier? What do you think? Is it just a little bit of noise added to the previous step? That is a natural guess, but sorry, it's not correct. Instead, the model is trained to predict the total accumulated noise that, when mixed with the original clean image, would produce that noisy image that you see at this step. And if that's the case, let's think about what your training data would look like. You start with a clean image, then you pick a random number of time steps, apply the noising process that many times so that you get a noisy version of the image. And because you know both the original clean image and the noisy result, you can figure out exactly which tensor of noise was added. Now that gives you a training example. The noisy image and the time step go in, and the tensor of noise that turns the original clean image into the noisy image is the target that the model learns to predict. But that raises an interesting question. If the model predicts the total accumulated noise in a tensor, wouldn't subtracting that noise from the input give you back the clean image. It sounds like it should, but remember, these models don't generate images in one jump. Generation happens through many, many small steps backwards. So why would you even predict total accumulated noise at all? And what would happen if you tried to remove that total noise all at once? There's nothing stopping you from trying it and finding out. For example, here's a noisy image from a model trained to generate bedrooms. And if you take the model's prediction of the total accumulated noise and subtract it all in one go, you get something that kinda sorta looks like a bedroom, but notice how blurry it is. And that's because the model's noise prediction is not perfect. If you bet everything on that single big guess, any little error can ruin the result. And that's why diffusion models don't subtract all the noise at once. So what you really do is a little more interesting. You actually still start with this estimated leap back to a clean image, but you add random values from a Gaussian distribution just like you did to create the training data, only this time stopping one step earlier than the input. So that will give you a slightly less noisy version. Repeat that loop again and again, and the static gradually fades away until a clear picture emerges. But why make that big leap back to a prediction about an original image in the first place? Well, if you predict between steps, you're sort of stuck trying to predict noise from noise when you're deep into a noisy image. There's no anchor there. By predicting the total accumulated noise, every training example ties back to the clean original image, and that will give the model something solid to learn from. Now, so far, you've been looking at the diffusion process itself, how images will emerge step by step from noise. But you might be wondering, what about prompts? These days, that's how most people think about diffusion models, with text guiding the process. Well, early diffusion models did not use prompts. They were considered unconditional. For example, a model trained on bedroom images would just take noise and generate a new bedroom. Or if it was trained on cat images, it would just make cats. But no control over the details, the results would not always be great, like this poor cat here. Later, researchers added conditioning. During training, the model saw not just noisy images and time steps, but also text descriptions. So when you give a prompt like a puppy on a skateboard, it can steer the denoising towards matching that. We'll come back to prompts more in the next video, and then in the lab, you're going to see that denoising process in action. I'll see you there. Welcome back. In the last video, we saw how diffusion models work, starting from random noise and gradually denoising it into an image. You also heard briefly about how models trained with images and their matching text descriptions could be used for prompt-based image generation. Now, it's your turn to actually make one of these models create an image from your own prompt. So we'll get hands-on and run stable diffusion step by step to see how it turns a prompt into an image. So let's look at the very first line of code here. Diffusers is a Hugging Face library that uses ready-to-use tools for running diffusion models. And Stable Diffusion Pipeline, the thing that you're importing, is one of those tools. A pipeline is basically a pre-built wrapper that bundles all of those moving parts of model inference into a single object. Inside it, Stable Diffusion is doing a lot. It takes your prompt, turns it into a text embedding, feeds that to the model with any other parameters that you set, runs the denoising process, and then decodes the result right back into an image that you can save or display. So instead of trying to wire up every step yourself, from tokenizer to scheduler to decoder, you can just call the pipeline in a single line of code, and it'll do the whole process for you. Now, this line of code points to the model that you'll be running in the lab, Stable Diffusion 2 Base. There's lots of different versions and newer ones like Stable Diffusion 3.5, and they can produce more detailed images, but they are larger models typically that take longer to download, and some of them require special permissions from Hugging Face. For this lab, 2 Base is a better fit. It's faster to load in your environment, easier to work with, and you can run it without going through any extra approval steps. We've seen how the pipeline handles all of the steps for turning a prompt into an image. And this line is where you actually load that pipeline with the model that you picked. The extra arguments here are just optimizations. Torch dtype equals torch float 16 and variant equals fp16 load the model in half precision which uses less memory and runs faster on a GPU with minimal impact on the results. Cache directory tells where to save the model files so it doesn't have to download them again later. And now let's examine this code. A generator is PyTorch's way of controlling randomness. Stable Diffusion will always start from random noise, and the generator is what creates that noise. By setting the seed, you're telling the generator to start from the same place, otherwise you'll end up getting random image results. So let's give the model something to create. Here you're passing three things. The prompt is that description that you want turned into an image. Then there's the number of inference steps, and this is setting how many steps the model will follow as it's refining that noise into the image that you want. More steps usually mean more detail, but of course it takes longer. And the generator is the random noise that Stable Diffusion starts from. Run this, and you'll get your first generated image. But a little note about generators and randomness. If you keep using the same generator without resetting it, each image will be different, because the generator keeps moving through its random sequence even though you set an initial seed. You'll see more about that in the lab. Now, there are a number of parameters that you can explore, and I found the best way to experiment with the Stable Diffusion pipeline is to look at its source code to see all of the parameters that it supports. For example, here's a couple that you can try in the lab to see what they do. First up is num images per prompt. Setting this to 3 gives us 3 different takes on the same prompt in one run. Each one will start with a different patch of noise, so you'll notice small differences in composition and detail. It's a great and quick way to compare variations without rerunning the pipeline over and over again. Next is num inference steps, and this controls how many times the model refines the noise before giving you a final image. Fewer steps will run faster, but your image can look rough or unfinished. More steps will add detail and polish, but of course they take longer to generate. And here you can see the difference. The higher step image has sharper edges and far more defined textures. Then there's guidance scale. This tells the model how closely to follow your prompt. Lower values will give it more creative freedom, and that can lead to interesting surprises. Higher values will keep it closer to your exact words. But if you push it too high, you can get results that looked overprocessed or unnatural. Finally, you have the negative prompt, and this is where you tell the model what you do not want to see. It's really useful for cleaning up common problems. For example, early versions of image generators often struggled with hands. So adding deformed hands to the negative prompt can help fix that. You can also use it just for fun. Here I was generating teddy bears eating pizza, but every image I generated had teddy bears eating pepperoni pizza. So adding no pepperoni pizza to the negative prompt helped change that to what you can see here. And those are just a few of the options you can tweak. There's plenty more if you want to peek into the pipeline source code. In the lab, you can also explore visualizations of the denoising process that you saw in the previous video, and I'll explain in more detail how to code these callback mechanisms. In many research and creative workflows, it's useful to inspect or save these intermediate changes to better understand, debug, or visualize how your prompt is transformed into a coherent image. One thing to notice here is that in Stable Diffusion, those intermediate states do not look like static, gradually resolving into an image the way that they did earlier in pixel space models. And this is because Stable Diffusion isn't polishing up the picture itself. Instead, it works on a hidden compressed representation of the image, known as one in latent space, that encodes high-level visual features rather than raw pixel colors, and it will denoise that instead. So when you see those weird, colorful blobs in the intermediate frames, you're looking at that hidden version decoded into an image format so that you might actually see it. It will look fuzzy and abstract early on, but as the model keeps working, those shapes will sharpen into a full, detailed image. The model uses its hidden version because it's much smaller than a full image, and the model will then run faster and use less memory. And that makes it more scalable and practical, but a little less intuitive to visualize at each step. And if you want to learn more details about diffusion models, check out the course resources for more information. In the lab, you're going to get to play with these parameters yourself and even visualize those intermediate steps using callbacks. It's a great way to see how your prompt gradually transforms into a finished image, and you can experiment with all of the creative ways that you can guide the process. So experiment, explore, and above all, have fun with your creations. Hello, and welcome to Module 4, Preparing PyTorch Models for Deployment. You've spent a lot of time training models throughout this professional certificate, and now it's time to prepare them to work in the real world and not just in your lab notebooks. So that means saving them, exporting them so that they can run in different environments, and optimizing them to be smaller and faster. In this video, you'll learn how to save and track your models, starting with simple serialization and version control, and then moving on to tools like MLflow that help you organize and manage models over time. Up until now, you've been training models inside a notebook for these labs, and that was fine for experimentation. But notebooks only save your code and not the models themselves. So if you spent hours getting one up to, say, 94% accuracy, and then the kernel restarts or the lab shuts down, your model's gone. So then you'll be back to running all of the cells again and going through the training loop all over again. And that's because your trained model will only live in RAM. When the kernel restarts, whether you close the lab or your computer rebooted, or maybe it just crashed, everything in memory disappears. So you need a way to save and load all the important parts of your model, and this process of converting those in-memory objects onto a form that you can store on disk is called serialization. So to save a trained model in PyTorch, you can just use the torch.save function. The first argument is the thing that you want to serialize, and the second is the file name. The file extension is arbitrary, but .pt is pretty common for PyTorch models. So your first instinct might be to save the entire model object, and this works, but it is tied to your exact code and environment. If the model's class changes name or moves to a different file, it won't load. If the class still exists, but you've changed it, this will silently restore the old version from the file, ignoring your edits. So even changing your Python or PyTorch version can sometimes break it. And that's why even the PyTorch documentation recommends saving the model's state dictionary instead, using this code. A state dictionary is just a Python dictionary mapping each layer's name to the parameters that it learned during training. These are your trained weights and biases, the actual learned numbers and not the architecture itself. As long as you can recreate the same architecture and code, you can load these weights and biases back in using torch.load as the input to the load state dict method on your model. And that way, tomorrow you can reload your model in seconds instead of retraining for hours or more. Another thing, and this is important, let's say you find a pre-trained model online that someone else has shared. Be careful. Torch load can execute arbitrary code when loading, so a malevolent model file could do things like deleting files, installing malware, or maybe even start mining crypto with your machine. So if you want to be safe, you'll want the weights only parameter set to true, and then it will only load the weights and biases and not any executable code. Weight only equals true is actually the default nowadays because of those issues. So saving at the end of training is great, but sometimes it's useful to save your model while it's training, especially at the end of certain epochs. Think of these as checkpoints where you can run torch.save, say, every 5 epochs, and note that in the file name with an F string. They're snapshots that you can go back to for a number of reasons. Maybe your model was already performing best at epoch 10 and you want to roll back. Or maybe you need to stop training for now and continue later. Or maybe you want to branch off and try a different experiment from a certain point. In all of these cases, the checkpoint saves you from starting over. In PyTorch, a checkpoint is just a serialized dictionary. You can store anything in it, but at a minimum you're going to need the current epoch, the model state dictionary, and the optimizer state dictionary, because remember, optimizers will store extra information that's needed when reloading a model in the middle of training. And you should also store the loss so you know how the model was performing at the time of the checkpoint so you can resume logging. It's kind of like saving your progress in a video game. When you load the checkpoint, you pick up right where you left off. Now, after a few training runs, you might have a folder that starts to look like this. Or maybe it starts to look a little bit more like this. Model, final, final, actually final. Well, does that look familiar? Which one was the good model? Which dataset was it trained on? What hyperparameters did you use? At the bare minimum, you can add information in the file name with f-strings, and including the accuracy is a great way to see performance at a glance. But the real pro move? Embed metadata right in the final saves or checkpoints. It's just a Python dictionary, so you can add whatever you want. Dataset version, learning rate, accuracy, training date, maybe even a note to yourself. PyTorch can save it all. But if you want to get really serious, and I know you do by now, MLflow is a powerful open source tool that can really level up your model management. You could imagine that, say, after a week of experiments, you might wind up with 30 checkpoint files and they all have cryptic names. Or you could have something nice and neat like this. Every training run automatically organized. Click the accuracy column to sort, filter by learning rate, compare 5 models side by side. Click any run to see its full history, and then download that exact model. Amazing. That's the power of MLflow. And in the following lab, you'll explore this platform and learn how to launch a tracking server. But first, let's explore some basics. The first thing to know is that MLflow organizes things around the idea of an experiment, and you can think of that as a project folder. An experiment is just a container where you'll keep all of your related work together. Later on, the individual training attempts you make will be stored inside this container. You can also attach tags to an experiment containing whatever you want, so it's easy to remember what it's for, and you can search for experiments based on those tags as well. Once you've created an experiment, the next step is to record your work inside it, and that's what a run is for. A run is one attempt, like training a model with certain settings. In a run, MLflow saves the parameters you used, the metrics you measured, and the model itself, so you can come back later and compare. But as you can imagine, there's a lot of details and settings that you can play with. And now you're well on your way to saving, checkpointing, and versioning your PyTorch models, which you can explore much more of in the lab and in the course resources. But what if you need to run your model somewhere that PyTorch doesn't exist? Maybe mobile apps, browsers, or embedded devices. And that's where model export comes in, converting your PyTorch model to formats like Onyx that can run on many different platforms. And we'll cover that in the next video. I'll see you there. Well, hello everyone and welcome back. In the previous video, we explored serialization checkpoints and using MLflow as an experiment tracker and model repository. Now, you don't just train and save models for fun. You've put a lot of work into a model that you're proud of. It performs well, and you know it's ready to be useful. Maybe to power a website, run in a phone app, or help make decisions in an embedded device. And that's what we're going to look at next, preparing your model for deployment, getting it ready to be used outside of your initial training environment. Because right now, your model is a PyTorch model, a set of Python objects that only PyTorch knows how to run. That's all very well if you control the whole environment, but many places you might want to run or use your model cannot run Python or PyTorch directly, and it kind of makes it incompatible with those systems. So to get past that wall, you need to make your model portable, able to run in many different environments, not just with Python and PyTorch. You'll do that by translating it into a universal format that other systems can read, and it can be used anywhere it's needed. That format that we're going to be using here is called Onyx, and that's short for Open Neural Network Exchange. It's an open standard used by many different machine learning frameworks to share models in a common language. By converting your model to Onyx, you're not just making it portable from PyTorch, you're making it part of a format that can move between frameworks and run on a wide range of platforms and devices. So once you've trained a PyTorch model, the export process creates an Onyx file. That's your model now in the standard Onyx format. Think of it a little bit like as packaging the architecture and the learned weights in a way that other runtimes can read it, and that's what makes it portable. The export itself is just a function call in PyTorch, but first, of course, you're going to need a model. Here, You know your model class, and as you saw in the previous video, you can use torch.load to get the model weights that were stored in a .pt file and use load state dictionary to load those weights into your model. It's very important to make sure that your model is in evaluation mode as well. And then Onyx is going to need to know the shape of the input to your model. And the simplest way to provide that is with an example input, like maybe a tensor with random values that will match the expected shape. So for example, with a single color image, that might be 1 for the batch size, 3 channels for red, green, and blue, and the height and width of the image. And now you're ready to export your model to the Onyx format, making it portable, so again, any Onyx-compatible runtime will load it and be able to do inference. Let's walk through what that looks like in code. The torch.onyx.export function takes a few key arguments. Let's go through them. First is the model that you want to export. Then is the example input tensor, so that Onyx knows the shape of your inputs. Next is the name of the file that you want to create, for example, model.onyx. Export params equals true tells PyTorch to include the trained weights and biases in the file, so you're exporting not just the model structure, but a fully trained model. Now we have the offset version. You can think of this as the version of Onyx that you're using. It's called offset because Onyx keeps a list of all the operations it can perform, things like convolutions or activation functions, in dictionaries that it calls operator sets. Each new version of Onyx will update that dictionary. So when you choose an offset version, you're really choosing which dictionary of operations your model will use. Now this one's interesting. Do constant folding. And here's what that does. If there's any math in your model that always produces the same output, instead of having the model calculated every time, it just replaces those calculations with a fixed value. For example, instead of always calculating 2 plus 2 and doing all of the operations for the math, it would just store it as 4, and then do that everywhere it applies. That gives you a smaller, faster model at inference time. Input names and output names let you assign names to the input and output tensors when you export the model. That way, they're easier to recognize if you look at the model in a visualization tool and easier to refer to later when you run inference with Onyx runtime. So instead of remembering something like tensor 0 or output 1, you could call them something like image and predictions. And finally, the dynamic axes parameter tells Onyx which dimensions can change size when you run inference. So, for example, if your model normally takes an input of shape 1 by 3 by 224 by 224, you might want to change the batch size to vary so that you can process more than one image at a time. So here we mark dimension 0 on both input and output as the batch size dimension, meaning that it can change while all of the others stay fixed. So now, once you've exported your model to Onyx, running is simple. First, load it with Onyx runtime by creating an inference session and passing in the name of your saved Onyx file. Remember earlier when we spoke about your inputs and naming them when exporting the model? Well, session.getInputs.name will just look up the first input and retrieve that name. It's as simple as that. You'll need this string later because Onyx runtime does not magically know which tensor in memory corresponds to which model input, so you have to tell it by name. This line is just creating a fake input, a NumPy array with the right shape and type, so you can run the model and see how inference works. In real use, you'd replace that with preprocessed image data. And then, to run inference, you just call session.run, passing in two things. First, the outputs that you want to get back, and then the inputs that you're sending to the model. Setting the outputs to none tells Onyx runtime to return all outputs defined in the model. For example, if you're working with an object detection model that produces multiple outputs, you can request specific ones by name, and you'll get back arrays containing just those values. If your model has only one output, it's safe to pass in none, and your predictions will be in the first element, which is 0, of the returned list. And that's all you need to get Onyx model up and running for inference. So now you've seen how to take a trained PyTorch model, export it to Onyx, and run it for inference. From here, you can explore more in the lab. Try running inference on different inputs or modify the output selection to match your needs. In the next video, we're going to start looking at how to make your models smaller and faster for deployment. We'll kick off with pruning, a technique for removing unnecessary parameters so that your model can run more efficiently without losing too much accuracy. In the last video, you saw two ways to prune a model: unstructured pruning, where you zero out individual weights, and structured pruning, where you remove whole convolutional filters or neurons. Pruning shrinks a model by turning off parts of it, sometimes those individual weights, sometimes whole blocks of the network. But there's another way to shrink a model that doesn't turn anything off or change your architecture at all. You see, most trained models keep every weight and every activation as a 32-bit floating number, and that's 32 ones or zeros for just a single value. And with millions or even billions of values, the space that they take up adds up fast. That precision is important during training because optimizers like Adam make tiny updates as training goes on. Those small steps need the precision of 32-bit floating numbers to settle into a good minimum of the loss function without overshooting. But here's the big insight. Once training is done and the weights stop changing, do you really need that much precision for inference? What if you just rounded the numbers a little, you kept them in the same range, but you used fewer bits to store them? It also seems sensible that the predictions might not really change. Neural networks already handle a lot of noise in the data, in the computations, etc. Most decisions are not balanced on a knife's edge where the tiniest decimal flip would change the outcome. And that's the big insight behind a technique called quantization. Instead of storing every weight and activation in the trained model using full 32-bit precision, why not store them using lower precision integers when running inference? So let's walk through a simple example of how that would work. Quantization is typically applied at the level of individual layers and not to the entire model at once. So let's zoom in on a small linear layer, and I'll keep it simple to say that it has just 4 weights like this. Since the model is already trained, you know exactly what those weight values are, and in practice, it's usually only the weights and activations that get quantized. Typically, the biases will stay in full precision, and because there's so few of them, they really don't add that much to the model's size, and even small rounding errors there could affect every output of a layer. The math works like this. Start with the weight that has the largest absolute value, and here we can see that's the 1.0412. Next, you're going to need a scale that makes that value fit inside the int8 range, and that range runs from -128 to +127. So that means you got 127 steps in either direction. So you set the scale by dividing that largest weight by 127. Once you have the scale, you divide each float weight by it and then round to the nearest integer. It's as easy as that. So now your weights are stored as int8 values along with a scale that tells you how to interpret them. And if you ever need an approximation of the original weights, you just multiply the integers back using that scale. So here's where it gets interesting. The whole point of quantization is that running everything in int8 can make inference smaller and faster. Now that works fine for the weights because they're fixed once the model is trained. But to really get those savings, the inputs and outputs of each layer also need to be int8. And you don't know these values ahead of time. So how do you quantize numbers that only appear at runtime? Well, one way to handle this is to take some sample data and run it through the model, not to train it, but to see what ranges of values will actually show up at each layer as the data passes through the network. From those observed ranges, you can find a scale that maps them into the int8 space. That way, when new data comes in later, you've already got good scaling factors for both the inputs and the outputs of the individual layers. And this process is called calibration, and it's the key step in what's called static quantization. Let's take a quick look at the code, and we'll get to explore more in the lab. So, if we're going to run data through a model, we need to tell it where quantization begins and ends. And the way you do that in PyTorch is simple. First, make a copy of your model and add 2 lines to the init, one for a quant stub and one for a dequant stub. Then, in the forward method, you drop them at the start and end of the data flow. Together, they mark where floats should be converted into int8 going in and where they should be converted back into floats coming out. That's simple. Now that you've added in the stubs, the next step is to load in the weights from your already trained model. You just copy its state dictionary into this new version, so it starts with the same learned parameters. Nothing's being trained again here, you're just moving the weights over. The next step is to set up your quantization configuration. Now think of this as choosing a recipe for how quantization should run on the CPU. And in PyTorch, it only runs on the CPU, not on GPUs. The default recipe is called fbgem, and that's what we're going to use here. So next, you're going to call prepare on the model. This step adds some little helpers called observers. They don't change how the model runs yet, they're just going to sit inside each layer ready to record values. And then comes calibration, where you pass some representative sample data through the model, not to train it, but just to let those observers watch. As the data flows through each layer, they'll record the smallest and largest values that they see in each layer. And that's how PyTorch figures out the right scaling factors, like you saw earlier for the weights. Also note at this point, everything is still running in float. Nothing's been quantized yet. You're simply laying the groundwork for choosing good scaling values later. Finally, you're going to call convert. And this is the step where PyTorch actually does the quantization. It quantizes the weights to int8, and for the activations, it uses the scaling values that we'll learn during calibration from that representative data. It will also swap in quantized versions of the layers so that all of the math will now run in int8. And those stubs that you added at the edges are now actively converting floats to ints at the start and ints back to floats at the end. After this step, your model is smaller and ready to run with faster int8 operations. Now that was quite a bit of setup, stubs, configs, prepare, calibration, convert, representative data, all of that stuff. But there's also a simpler path known as dynamic quantization. And here you just take your trained model, put it in eval mode, and call one function, quantize dynamic. You can tell PyTorch which layers to quantize, either by type, like nn.linear, or by naming specific layers, and activations are quantized on the fly during inference instead of using pre-computed ranges from calibration. Of course, if it's that simple, there must be trade-offs. And there are two important things to note. First, not every layer type is supported in dynamic quantization. For example, convolutional layers like conv2D will not be quantized dynamically, they'll just be skipped. So if you need your convolutions in int8, you'll want to follow the static path that we covered earlier. Second, just like static quantization, dynamic quantization will only run on the CPU. So GPU acceleration with CUDA is not supported here. So when should you use which approach? Well, dynamic quantization is that quick win. Minimal code, no calibration, and it works really well for models with large linear sections like RNNs or transformers. Static quantization, on the other hand, takes more setup, but it pays off with bigger speed and memory savings, especially for things like CNNs, where there's lots of convolutions. In the next video, you're going to go one step further with quantization-aware training, or QAT, to squeeze out even more performance while keeping accuracy high. And then you'll see it all in action in the lab. See you there. Previously, you saw how you can shrink a model with quantization. Instead of keeping every weight and activation as a 32-bit float, you could store them as 8-bit integers. And that often makes your model much smaller, sometimes close to 1/4 of the original size, and it can also speed up inference. So far, though, you've only seen this done after training. You let the model learn in full precision, and then only after that you rounded it down for inference. That works, but think about what happens when you take numbers that your model tunes so carefully, and then you suddenly round them to fit into 8-bit buckets. Some of the predictions can shift, and accuracy can drop. That's because your model never saw those rounded numbers while it was learning. But what if you could let your model train while seeing 8-bit values so it could adapt its weights and keep accuracy high? That's the idea behind quantization-aware training, or QAT. Instead of waiting until the end to quantize, you take a pre-trained model in full precision and fine-tune it using simulated 8-bit values so it can adapt before converting to real int8 for deployment. So, first, your initial setup is the same as you saw for static quantization in the previous video. In your init, you'll define the quant stub and the dequant stub. In your forward method, you'll wrap the data flow with those stubs. Now, there's a few more steps to set up a QAT model, and you'll explore those fully in the lab. I'm going to skip ahead to the part that shows you the core idea, and that's when you call prepare QAT on your model. When you do this, PyTorch looks at your model and adds some extra steps at the key points, like the stubs at the start and end, but also inside the different modules. So let's start right at the top with that first stub. Your model is in training mode, and a batch of data comes in. One of the steps added here is an observer, just like we saw in static quantization. It's watching and recording the smallest and largest values in the incoming batch. As more batches pass through, it updates those running min and max values whenever it sees something new. And with those values, it can calculate a scale, the factor that you'll use to map your float32 numbers into int8 buckets. So with that scale in place, there's now a new step, something called a fake quantization module. This module uses the scaling value to fake int8 by converting the float32 into a rounded int8 and then immediately dequantizing it back to float32 using the same scale. So it's still a float and your model can keep training like normal, but it's as if it just passed through an int8 bottleneck. For example, say you have an activation value of 0.125 and the scale is 0.041. The fake quantize returns the value divided by the scale and rounded to 3. It then immediately dequantizes it back to the float32 using the scale, so 3 times 0.041 equals 0.123. It's pretty close to the original 0.125, but not exact. And that tiny difference is what your model learns to handle. So now let's take a look at what happens inside a layer like a linear layer when you've got both activations and weights. The activations coming into the layer are already float32 values that have been through that fake quantization once, so you don't need to add another step before they enter. Now let's talk about the weights. In static quantization, the weights were fixed because you only quantized them after training was finished. But here, training is still going on. So that makes our situation a little different, but not wildly different. You're going to use the same steps. You're going to find the min and max of the weights, calculate a scale, and use that to do quantization. The twist is that this has to happen every batch because those weights are still changing. So for each forward pass, PyTorch makes a temporary, fake quantized copy of the weights. It quantizes them as if they were int8, and then immediately dequantizes them back into float32. That copy is what the layer uses to do its math. Meanwhile, the original weights remain in full precision, so gradients can update them during backpropagation. And finally, the outputs. Just like in static quantization, you can still quantize the output of a layer so the next one receives values in int8 with a known scale. And that keeps the whole model in step. But in QAT, of course, this is only simulated. The outputs are fake quantized as if they were int8 and then immediately dequantized back to float32 so training can continue as normal. Now, there's one more nuance. In a common sequence like convolution, batch normalization, and then ReLU, if you leave those as 3 separate steps, prepare QAT will insert a fake quant step after the convolution. Then, nothing extra happens. It also adds extra noise and doesn't quite match how you'll run the model later. The fix for this is simple. Before you prepare for QAT, you use fuse modules. This combines those steps into a single block, so you only quantize once at the end. And now there's only one fake quantization step at the block's output, and the weights inside will still get the fake quantization treatment as well. You get a cleaner training signal and a layout that mirrors the int8 model that you're going to convert to. And that's the big picture of quantization-aware training. While the model is still learning, PyTorch inserts those fake int8 steps around weights and activations so the network gets used to rounding noise, and you sometimes need to fuse layers to make it more accurate and efficient. Of course, there's a bit more setup in code. You need to include your stubs, fuse your layers, load in pre-trained weights, prepare, and fine-tune the model. There's also some details to pay attention to during training and when you finally convert the model into its final int8 version. You'll get to walk through this entire process step by step in the lab. There, you'll see exactly how to set up QAT in PyTorch. You'll see what each step does and how to check the results for yourself. So let's put all of this knowledge into practice. You've now reached the end of the deployment module, and you know how to save, export, prune, and quantize your models to get them ready for the real world. And speaking of deployment, this is the moment that your skills are ready to deploy too, out of the notebook and into the real world. Because not only is this the end of the deployment module and course 3, it's also the end of the entire PyTorch for Deep Learning professional certificate. Congratulations! Think back to where you started, with a single neuron learning a simple pattern. From there, you built full neural networks, learned how to manage messy real-world data, and mastered PyTorch's workflow. You went on to optimize and tune models, adapt pre-trained architectures for vision and text, and build efficient training pipelines. And finally, you explored custom architectures, advanced vision and language techniques, and the steps needed to prepare your models for deployment. And you didn't just learn about these ideas, you put them into practice. You've written the code, you've debugged it, you've trained models and you've optimized them. And that means you haven't just gained knowledge, you've proven that you can apply it. And these are the same skills that practitioners and researchers use every day, and now they're yours. You can take them into your own projects, your own career, and your own creative challenges. So take a moment, be proud of how far you've come, and then keep going, keep building, keep experimenting, and keep deploying your skills into the world. We cannot wait to see what you create next.